Hi everyone. We are very happy to have Mahdi Haghifam speak in our seminar today. Mahdi is currently a postdoc in the CS department of Northeastern University, where he is hosted by Jonathan Ullman. Mahdi got his PhD from the University of Toronto, where he was also a graduate student researcher at the Vector Institute for Artificial Intelligence. During his PhD, Mahdi worked as a research intern in the privacy team of Google Brain and ServiceNow Element AI. And Mahdi's research focuses broadly on the statistical learning theory and differential privacy. And today he will tell us about the information complexity of the stochastic convex optimization. All yours, Mahdi.
Uh, Thank you. Thank you, Said, for the invitation and introduction. I'm really happy to have a chance to talk about our recent work on information complexity of stochastic convex optimization. Before I get started, so I don't know, feel free to ask question anytime. I'm not trying to give the very technical the talk. I just want to discuss the high level ideas. So feel free to ask question about specifically this some the jargons that you're not sure about. Yeah, that would be awesome. So before I started it, this is a joint work with Idan Atias from Ben Gurion University, Carolina Jogeta from Google, Roy Livni, faculty at Tel Aviv University, and Dan Roy, who's a faculty at Toronto. Okay, what is the high level idea of this talk? In this talk, I want to tell you about the very the complicated connection between learning and memorization. So probably from the machine learning 101 course, we know some statement of this form that learning irrelevant information in training set will hurt generalization performance. Generalization means that the performance on unseen sample. And probably in a machine learning 101 course, you have seen such a plot that we have a set of points. We want to fit some polynomial to it. We can start with degree 1 polynomial. Our training set are red curve. It is probably not really good in terms of fitting the training set, but it seems that the performance is roughly the same if we take a fresh sample, which shown by orange. And you may also try the very high degree polynomial degree 3. As you can see, it fits the data really well, but it seems that the performance on unseen samples are not good. So, and by looking at these type of plots, we see that it seems that in a regime that the number of parameters is much more than number of examples, bad thing can happen. So in this talk, we want to understand how universal such a statement is, or in a very cryptic way, the goal of this talk is to tell you memorization does not make a learning algorithm to not generalize. This is the very high level idea behind this talk. So let me start from I'm pretty sure most of you know the problem of learning from data. I use this as an opportunity to introduce some notation that we will use. So let's consider the classification task. We want to classify cat and dog. We model these tasks as an unknown data distribution. And the goal is to come up with a predictor, which is which is a rule that convert image to a label with a small population error. Population error means the error on unseen example or a fresh example on average. So that's that's everything is good. If we know the data distribution, we can directly minimize this the population error and find the best predictor. However, the challenge is we don't know the data distribution, and the only information we have is through a set of a IID sample, which is known as training set. And we define a proxy for population error, which is defined as training error, which is the empirical error of the predictor on these samples. And we have also this term of function class, meaning that the set of predictor we have under consideration, meaning that our search space is like the set of find some like the set of predictors. And there's a concept of learning algorithm, whose role is to convert training set to a predictor, basically in a function class. Basically, this is like the all ingredient of a learning problem. We have unknown data distribution, training set, we feed it to a learning algorithm to obtain a predictor. So the question is how to measure the performance of a learning algorithm. Like the fundamental measure here is a notion of called excess error. Excess error is defined like this, meaning that what is the difference between the achievable population error of a learning algorithm compared to a comparator term? And this comparator term intuitively, meaning that you can view the notion of excess error as like some game in which we compare population error of the algorithm with population error of a player who knows the data distribution exactly and can compute this minimum exactly. So this is the notion, right? So basically we want to compete with someone who knows the data distribution. The disadvantage of like the learning algorithm is that it doesn't know basically the data distribution. And basically the idea is how should we use training sets in order to gain useful information about the training set so that we can achieve a small excess error. In order to motivate this idea, there is a very fundamental decomposition of excess error in these two terms. The first term is saying that if you want to, as an upper bound, if you want to achieve a small excess error, try to fit the training data as good as possible. And this second term is saying that we need to fit the training data, and at the same time, the performance of the algorithm on unseen sample, which is captured by this second term, and the samples from the training set should not be that much different. Basically, if you look at like this type of decomposition, it's basically saying that we need to use data, but also at the same time, if you use data like in a very bad way, we may have the first term may be small, but the second term may be large. And it basically, then the question is, how much information must a good learning algorithm retain about the training set? So in more formally, in this talk, we want to understand the following. If you look at the learning algorithm as some sort of like communication channel, which takes as input the training set and output a predictor, we want to understand like what is this curve, meaning that what is the cost of achieving a small excess error in terms of the information of the output of the output predictor, the information that the output predictor contains about the training set. Basically, the goal of this talk is that what is the right trade-off here. The two questions we're asking, what's the trade-off between achieving low excess error and information usage? And the second question is, what is the operational meaning of this trade-off? For example, probably if you're familiar with learning theory, you have seen lots of results that what is the trade-off between the sample complexity, meaning that how many samples we want, and excess error. For these type of things, there's a really physical meaning the sample complexity means that how much sample you need to ask from some expert who can label, for example. Here, we want to understand, if we understand this information, the learning trade-off, what is the physical meaning of this? In this work, we answer both of these questions, I guess, somehow completely in the setup of stochastic convex optimization. This is the plan for this talk, and basically to tell you about this trade-off. In the first, I want to spend some time to motivate the idea why stochastic convex optimization is a good framework for studying such a question, right? This is, until now, I haven't told you about why stochastic convex optimization, why it's relevant, right? So you can think of this image as the zoo of learning problems. We have binary classification in pack sense. And we have like modern deep learning, and if you're familiar with some of this literature, there are like there are things that they are not like very aligned with each other. In the next couple of slides, I want to tell you that we have a theoretical model which is called stochastic convex optimization. And in this model, we still can talk about like the learning in a in a very, very packed sense, distribution free sense. And at the same time, it has lots of similarity with the type of things we see in a modern deep learning. And this is like the plan, right? I want to motivate you that like stochastic convex optimization has some similarity to the modern deep learning. And this is why I personally think it's a very interesting like the framework to study lots of things before going to deep learning, right? So just an overview, we have like the binary classification, the error, the difference, like the error is a 0, 1. Again, the question is, what is the algorithmic landscape for binary classification? There's this very seminal paper. We completely know what to do. And I'm not going to tell you about like everything here. The important things here is that if we think of VC dimension, which is for the purpose of this talk, assume VC dimension is the number of parameters that we require to basically represent each function. What it's saying is that overparameterization is bad, meaning that if you want to achieve XSR of epsilon, you need much, much larger number of samples in order to do that. Another thing is that learning is based on what you see is what you get, meaning that setting computational efficiency aside, it basically tells you that whatever, if you have enough sample, whatever you see, meaning that like whatever you see in terms of the training error is a good proxy for population error. And the very simple landscape, there is no algorithm involved. You just need to minimize the training error as in the best possible way. And basically looking at that decomposition we discussed, it's saying that you just need to minimize the first term. And the second term cannot be too large because we are in a regime, we are not in the overparameterized regime, and we have much, much more sample than the complexity of class. We also know more in this setup because we have approach to like the minimized training error without heavy dependence on data on the training set. This type of things is studied in like in the binary classification under the name of sample compression scheme. The idea is so simple. For example, if you consider SVM, in SVM, if you look at like this, all of like this KKT condition, it's easy to see that the output really doesn't depend on all the training set. The output only depends on finite set of samples, which is known as like support vectors. And you can also see it like in this simple case of threshold. And in a learning theory, this type of algorithm has a name, and their name is sample compression scheme. The idea is that if you can view a learning algorithm as some sort of like, as two-party setting in which the first item try to compress the sample into some subsets, and the second part is just looking at this and output something with the condition that like the output achieve minimal error on the whole sample. I'm not going into detail. There is a very, very like the breakthrough result by Shai Moran and Amir Yahudayov, in which they show that for every VC class, I mean every class that we can do the binary classification, there exists a compression scheme in which the size of like this compression set is constant in VC dimension. And it's saying that like even though we need 1 over epsilon square sample, only like some constant number of them matters. And if you're interested, we had the paper from a couple of years ago to study the impact of this on information usage of algorithms. So far in binary classification, what I told you is that overparameterization is bad. We don't need to interact with all the samples. there is no algorithm involved. You just need to do like the training error minimization. And the question is, how does this type of observation compare with what we observe in modern deep learning? Probably you have seen this paper many times. I'm not going to talk in details about this paper, but definitely this paper puts lots of new observation on the table. What's one of the things they study in this paper? They did an experiment. They take an MNIST data set, and instead of looking at real label, they take a random label. They put a random label on these images. For example, instead of 4, they have 2, 0, 3, and they basically create a garbage data set. And so one thing that's important here is that there is no information in this data set. And it means that if we have a network that can fit this data, it means that this network can pick up lots of useless information. And this is what they did, right? They just trained a neural network, and they observed that if you train a neural network for a very long time, it achieves 0 error, 0 training error, at the same time that the best test error you can achieve is 90%, because there's no information. It's like predicting the coin flips. And you can see that there exists like the distribution such that the neural network achieves 0 training error. And at the same time, the population error is like 90%. This is the gap, right? And this is like the result I show you. There's a 0 training error while the population error is no better than random guess. And there are like the other results by Neishabur, Tomioka, and Cerebro, in which show that sometime we achieve 0 error, and also population error is small. And these two things, what they are telling us is that at least in deep neural network, we are in a regime that what you see is not what you get. In the sense that we can have a small error, but this small training error can come with like the complete memorization. And basically, on the other hand, if we use good algorithm, we can have a 0 training error with small population error. So again, if you're looking at like this decomposition, it pretty much matters how we basically minimize the training error. And it's basically like and there's a long line of work on understanding why a specific learning algorithm can do a learning in a good way. So basically, our goal is to, I guess, the whole community's goal to understand deep neural networks. And we observe that there are these type of uniform convergence, or like the working in over-parameterized regime, is not something that we can explain using binary classification. So before like this Zhang, Benju, Hart paper, around like 8 years ago, there was this paper at Colt under the name of stochastic convex optimization. In this paper, the authors study a very idealized setting. The goal is to, again, the problem is finding population error. And now the difference is that the loss function is convex. We have loss function takes 2 values, predictor and sample. We have unknown data distribution, and this type of learning problem includes lots of things such as logistic loss, SVM, and etc. And again, the goal is to minimize this population error with access to a training sample. In this paper by Shalef Shuar, Shamir, Cerebro, and Sirdaran, they ask the following question: what is the algorithmic landscape for stochastic convex optimization? In the sense that if we want to achieve small excess error, how can we do it, and what is the sample complexity? There's a result on this that I would like to call anti-fundamental theorem for SEO. And the first thing they try is to say that what is the statistical properties of the training error minimizer. What they observe is that the sample complexity, the only thing that matters is scale with dimension, right? Meaning that the optimization, the dimension of the optimization parameter affect the number of sample you require. Meaning that if you just minimize the training error in an arbitrary way, you need dimension-dependent sample complexity. And basically, if you look at like the construction here, they show that if you have not enough sample, meaning that your sample complexity is not scaled with dimension, you will be in a situation that like the training error will be small, but the population error is large. Very similar to type of observation we have in like deep neural network. Another thing also they study is the SGD, right? This is convex. From the optimization theory. We have lots of results, and let's understand what is the sample complexity of SGD. And surprisingly, what they observe is that when you use SGD in the SCO setup, suddenly the dimension dependence disappear. Then it means that basically, if you use right algorithm, you can learn SCOs without paying for dimension, in the sense that we can be in a highly overparameterized regime. Dimension can be much larger than sample complexity, and still we can learn. And this is exactly the type of things I like about SCO, is that we are in the regime that like the learning algorithm, at least we know that if you use a specific learning algorithm, you can do completely different things than use like the arbitrary training error minimizer. And the goal of this talk is to understand like these type of algorithm a little bit better, in the sense that even though we are an overparameterized regime, what is the cost of like the using very small number of samples in terms of the learning information trade-off? Is there any question until now? Okay, so let me go more into detail of like what we exactly study in this paper. The main question of we study in this paper is we want to understand like the information learning trade-off for SCOs. We need this definition, which we call epsilon learner. Epsilon learner means that you have an SCO problem, meaning that a set of like the parameters, subset of RD, loss function, and we say a learning algorithm epsilon learn with sample complexity of n. If given enough sample, it can achieve small excess error for every distribution. This is like the class of good algorithm, right? Meaning that, and we know this class of algorithm exists, for example, SGD, and as we can see, the sample complexity doesn't depend on dimension, just depend on epsilon. We know such a learning algorithm exists. And the goal of this work is that given an SCO problem, which is like the set of parameters and the loss function, what is the best algorithm in this epsilon learner in terms of the memorization, right? Again, if you remember like that trade-off between the plot of trade-off between information, memorization, and excess error, we want to understand what is the fundamental trade-off there, right? Until now, I haven't defined like how we measure memorization. My goal in the next two slides is to basically formally define like the notions of memorization we use in the paper. Okay, how we measure like some sort of memorization? The first thing is like membership inference, right? So probably you guys are familiar with this, but again, let me go over the definition. This is like the this is basically the ingredient of a learning problem. We have a data distribution. We take some samples. We feed into a learning algorithm to obtain a predict. Assume we take also a set of fresh samples from the same data distribution. Just S tilde n has the same distribution as training set, but it is independent of everything else, right? And consider the following game we play with adversary. There's an adversary. The adversary doesn't know the exact description of a learning algorithm. Adversary only has access to the output of like this output predictor theta hat. And we want to play this game with the adversary. We want to flip a fair coin. And if the coin is 1, we show a sample from true training set. And if the coin is like 0, we show a sample from like this ghost set or held out set. And the adversary, by only looking at like by looking at this sample and the output predictor, it wants to basically decide whether, basically the question is, it wants to, by looking at theta hat and z, the adversary needs to decide whether this sample was part of a training set or not. This is like the game we want to play for n round. And how we measure the performance of an adversary. First of all, we need an adversary to have a small error probability, in the sense that we say adversary is kissy sound if the probability that in this end round of the game, adversary accuses a sample from a held out set as like the training set is less than kissy. Meaning that we want an adversary to have, when it says like 0, when it says like it was part of a training set, we want to have confidence in it. But if you look at this definition, achieving this is simple, right? The adversary can always say, no, it was not. This sample was not part of a training set. Because of that, we impose the second condition. We say adversary certifies a recall of m examples if in this end round of the game, we always show the adversary a sample from a training set. It can, with a constant probability, it can identify at least m examples, right? So basically, this second condition basically rule out the adversaries that always say no, right? This is not part of training set. And basically, one way to measure and one way we will use to measure the memorization is saying that if we fix kissy, what is the largest m? Among all the adversaries with a fixed, like our kissy sound adversary, what is the largest m, right? What is the maximum number of what's the number of like the recall, right? This is our first notion, which is very similar to, I guess, intuitive understanding of memorization, and also it has lots of connection with privacy, so on and so forth. Our second measure is more information theoretic, like the notion, and it is based on a framework of a work of Stanke and Zakentinu, and what they call as CMI. Let me try to introduce it more formally. CMI is what is a CMI? The right way to think about a CMI is a CMI is an approach to measure the information usage of a learning algorithm. Okay. And in order to define it, we need some additional structure. Define a membership vector as a vector of size n is the training size of samples, and in which each element comes from like the binary half. And they also define supersample, in which it is like the table of size 2 by n, and each element comes from a data distribution, IID and IID sets. Using membership vector and supersample, we pick one sample from each column, and then we form a training set. Basically, because this is 0, we pick this one, because 1, we pick this one, so on and so forth. We feed it to a training set, to a learning algorithm, to obtain an output. Again, I need to emphasize, this is not the way we train a model. This is only because of like a notion that we want to that's like Thomas and Lydia defined. And what they did is that they defined CMI, or conditional mutual information of a learning algorithm, with respect to a data distribution D, as the mutual information between the theta hat and membership vector condition on supersample. What is the intuition of this? Basically, if a learning algorithm depends too much on the training set, then an adversary with access to theta hat and supersample can identify membership vector, in the sense that it is easy to tell what was the membership vector. Basically, it tells us that if by looking at the output, you can recognize the training samples out of like two options that we have, it means that the CMI is large. On the other hand, if, for example, consider learning algorithm that doesn't use the data, right? Then the CMI is 0 because theta hat is independent of everything else, and then it is 0. And the reason that we care about, the reason that like the whole community care about this phrase, this notion, is that this notion exactly upper bounds the generalization error or population minus training. Basically, in this paper by Stank and Zakentino, they show that CMI divided by n exactly upper bounds the second term. And basically, this is very intuitive, right? If you don't heavily use the data, then the generalization error has to be small, right? The generalization error is large when we use data heavily and we start picking up irrelevant information. So, and this is like the second way to measure basically this is like the second way to measure information and memorization.
Can I ask a question?
Sure.
About this CMI, if we are optimizing over a VC class, then is this CMI going to be the VC dimension, like the VC bound?
Yeah, that's a very good question. So in the paper by Thomas and Lydia, they show there exists an algorithm with CMI of VC log n. And basically, then they ask these questions. There's an cold open problem on this, that when we can remove log n, there are results which shows that for some subset of VC classes, meaning that, for example, for example, finite star number classes, this log n is removable. But we don't know. The answer is not clear. We don't know whether like this is VC log n or VC. There's a log n here, yeah. But if you're okay with log n factor, there exists an algorithm such that the worst case CMI over distribution is no more than VC log n.
But the algorithm, it's not like they construct the algorithm, or is it just it exists? Like,
yeah, unfortunately exists, yeah.
Because in the classical settings, like the ERM you use ERM and it achieves the VC bound, right?
Yes. The problem with in the paper, they had to do ERM combined with axiom of choice. Yeah, it's like a little bit problematic. Yeah, it's easy to see that you cannot. So yeah, in terms of like some result we have in terms of like error, excess error, if you use any ERM, it's going to be like sample complexity. There's a log factor, but it's not much worse than VC. But in this paper, they show that this result cannot be achievable by arbitrary ERM. You need to construct a very specific ERM.
I see. Thank you.
No problem. And yes, and basically, yeah.
Okay, can I ask you another question about this paper, because it's been a while since I've seen it, but I don't remember. Can you use differential privacy to bound the CMI?
Yes.
I think that's like one of the things. Okay, that was just a question.
N epsilon square. If you have epsilon dp, it is something like n epsilon square.
Okay, that makes sense. Thank you.
Yeah. And yes, and basically, again, what is the intuition here? If you want to achieve a small CMI, you can say, I don't want to use data. But the problem is, if a learning algorithm doesn't use the data, it is impossible to achieve a small excess error. So what we want to understand is that if we achieve a small excess error, is there any way to minimize CMI? What is the minimum possible CMI achievable? This is like the question here. So let me go over the main results. I will start with like this result on CMI. What we showed is the following. There exists a loss function that is Lipschitz, defined over the ball of radius 1, such that for every learning algorithm that epsilon learns with the sample complexity n, which is independent of dimension, in a highly overparameterized regime, note that n is, think of epsilon as like 1/10. It seems that when d is much, much larger than the number of samples, in a highly overparameterized regime, there's a cost we need to pay in terms of the information. We show that there exists a data distribution such that CMI is 1/epsilon squared. So what is the intuition behind this result? So let's first understand what is special about 1/epsilon squared. 1/epsilon squared is, for this class of function that we construct, is the optimal sample complexity for achieving excess error. If you view as CMI is basically CMI, okay, consider these, okay, let me get back to this. So one thing I forgot to mention is that the worst case, the upper bound for CMI is n, right? Because CMI, you can upper bound it by entropy of U, and entropy of U is n. So CMI in the worst case can be n, right? Good. So what this result is saying is the following, is that for this specific loss function that we construct, you only need 1/epsilon squared sample, no more than that. And when you have an extremely sample efficient algorithm, meaning that the algorithm that only use 1/epsilon sample, CMI is maximum. Meaning that in terms of the information leakage, CMI cannot distinguish between what you're doing and complete overfitting. Achieving CMI equal to n is easy, right? You can just overfit. But it's saying that in an overparameterized regime, when we want to be extremely sample efficient, we need to basically, any algorithm has to heavily depend on the data in the sense that the CMI will be large. And also, if you care about, like, if you're following the CMI literature, CMI basically was introduced as an approach for unified approach for proving generalization bound. And our results showing that there exists at least a separation between stability framework and CMI in the context of SEO. We show that using CMI, we cannot basically study the generalization performance of the sample efficient learning algorithm in the context of SEO. This is our first result. The second result, which is again, this result relates to why should we, okay, so until now it is very like theoretical, meaning that yes, CMI is interesting, but what is the physical meaning of this result, right? We show that there exists a SEO problem with a Lipschitz loss, and there exists an efficient adversary, such that notice that the policy of that, like the algorithm of adversary is independent of the learning algorithm, in the sense that if you think of like the two-player game, the adversary can say, oh, this is my strategy. And then we show that even if you know the strategy of adversary, there exists a kissy sound adversary such that it certifies a recall of 1/epsilon squared sample. And again, recall that minimum number of samples required for epsilon learner is 1/epsilon. Again, this means that for extremely sample efficient algorithm in a highly overparameterized regime, the situation is much, much more different than, I don't know, SVM, in the sense that we need to use every sample in a very like the learning algorithm needs to heavily use every samples. There is no such a thing that there's a subset of samples that are useful. It says that basically there exists an adversary that can tell you like, yes, these are the samples you use. If you're happy with like the notion of membership inference we defined, which is very standard, it says that the adversary can like can distinguish the samples you use. And there are extension of this result. You can ask what happened in strongly convex case, because in a strongly convex case, we need less samples. Same result holds, that CMI become 1 over epsilon. And again, there exists an efficient adversary which certifies the recall of 1 over epsilon samples. Our second result saying that improper learning doesn't help. And for example, if you know some result in differential privacy, which shows that if you can, for example, GLM, in the context of GLM, if you can output something outside the ball, you can completely remove dimension dependence, for example. But we show that in these contexts, improper learning also doesn't help. So one question is that probably you guys have heard of differential private. So one question is the following, right? We have differential private approach for stochastic convex optimization, thanks to the result of like this very, very, very important paper from NeurIPS 2019, which says that basically what they do is that they ask, can we do the DP, can we learn DP, can we perform SCO under DP, differential privacy? I'm not going to define DP and stuff, but let me tell you what is the difference between this result and our result. What they show in this paper is that sample complexity of differential private SCO depends on dimension dependence on dimension is square root D. Consider privacy and excess error as constant. I'm not going, this is very unfortunate because I used epsilon for excess error, but yeah, I'm so sorry for this, but anyhow, treat privacy and epsilon as a constant now. Epsilon is the excess error guarantee that we want. What they show is that you need a square root D sample to do anything interesting. What we showed, on the other hand, is the following. If you look at consider all the dependence of the dimension and the number of samples, right? So let's say you're in a regime that you have more than a square root D samples, right? In a dimension dependence way. In this upper side of the curve, from this result, we know that DP learner exists. Like DPSGD, for example, can do this. And when you can do stuff with DP, then we cannot talk about like this memorization in this heavy manner. What we showed is that, yes, if we don't care about differential privacy, we know there exists algorithm with, for example, SGD and SCO. The sample complexity doesn't depend on dimension, meaning that is a constant. We show that even if you have a little bit of dependence on dimension in terms of sample complexity, DO to the power of 1 over 4, meaning that if you are in this part of the curve, it is not like you're going to lose the membership of one sample. You're going to lose membership of lots of samples. This is something I would like to emphasize, is that when we are saying a learning algorithm is not private, even if learning algorithm depends heavily on one sample, it rules out privacy. But what we show here is that if you are in a highly overparameterized regime, meaning the sample complexity dimension is much larger than number of samples, it is not the case that you're going to leak one sample. You're going to leak lots of samples. Any question on this? And this is why I guess, and there's this orange curve. We don't know what's going on. Is it like the artifact of our analysis? Is it like something more like the fundamental going in this regime of like D over 1 over 4 to the square root D? We don't know. What we know is that if you give me a sample, if you give me an algorithm whose sample complexity is below this red curve, our result basically says you're going to leak lots of stuff. And if you are greater than square root D, you can do DP, but here it's not very clear. Sure.
So was it, if I remember correctly, like your theorems started with there exists a instance or a loss function or something.
Yeah.
So for a particular loss function, there exists an adversary that can leak like 1 over epsilon squared of the. So it's not like for any loss function under that curve is.
mean, such a result is not possible. For example, you can consider loss function that is like 0, right?
Ah, yeah.
Yeah, that's a very good question. The question is, yeah, one thing is that these results are still in a min-max type of setting. You want to say exists, but understanding like what can we say about like more like relaxed loss function, logistic loss stuff? Again, it's not very clear.
I see.
Yeah, I agree. That's a very good point. Yeah, that's what I guess I need to mention is that it's so this result is not saying for every distribution. It's saying that for there exists
I
a
see.
loss such that for every learning algorithm there exists a data distribution. Yeah.
Mhm.
Even yeah. Good. So let me check. Okay, is it 12:51? I will tell you about a little bit of like the proof overview. The loss function is this loss function if you're familiar with SCFT. I'm only going to tell you about the proof for a strongly convex setting. Unfortunately, the proof for non-strongly convex is complicated and also requires me to introduce more notation that I'm not going to do it. So this is the loss function we use.
Mhm.
What we showed is that for every epsilon learner and for every distribution, this is like universal result, the output needs to have a high inner product with the unknown distribution mu of like the data point, right? So theta hat and mu needs to have some noticeable inner product, right? Again, remember our assumption. Because we are learning, right? Because we do learning, theta hat, the algorithm doesn't know the data distribution, right? So where does this correlation come from, right? It means that like the output of the algorithm needs to gather some information about the unknown data distribution. And what we used is this technique in like from differential privacy literature for proving lower bound, which is known as fingerprinting lemma, which says roughly the following. It says that the cost of high accuracy output is correlation to a training point. Basically, what they're saying, let's say fingerprinting lemma in a very, very high level idea is that the correlation to unknown data to the mean of the unknown data distribution can be translated to correlation to samples. This is basically the basic thing. This is the idea. It means that if you don't know the data, if you don't know if your algorithm doesn't know the data distribution, in order to have the correlation with the unknown mean of the unknown data distribution, we need to have a correlation to the training points, right? This is fingerprinting lemma in a very, for example, what you can see is that if theta hat is independent of samples, then the left-hand side is 0, right? So what it's saying is that we need to have a little bit of correlation. It is not possible that we can say correlation doesn't exist, right? And the question is basically how we can transform it into the information lower bound or membership. This is not our work. I guess this is some sort of corollary of previous form. And what we showed also is that when the dimension is extremely large, if z is independent of theta hat, then this random variable is a sub-Gaussian with a very, very small variance proxy, meaning that with a very high probability, if z is independent of theta hat, again, recall that this membership attack that we have some fresh samples, this random variable is concentrated over 1 over n square. There's very, very small correlation, and this is thanks to our dimension. If dimension is small, such a result is not possible. So what we learn is that if a point is not part of a training set, correlation is small, and sum of the correlation of training point and the output is large, right? So what we need to show is that whatever learning algorithm does, it needs to have some correlation to some subset of training points. And again, for example, recall like the CMI definition. The CMI, we have like the 2 sample in each column. You can, I don't know, for example, by using Fano's inequality, you can view the lower bounding CMI as doing some hypothesis testing that we want to, by looking at theta hat, we want to identify whether like the we use Z01 was part of training set or Z11. And what we show is that the first sample, as a first part, is that the CMI can be lower bounded by the number of columns with large difference between the correlation. Consider this inner product as a measure, as like test statistics. And we show that if the number of columns such that for one of the samples, these test statistics is large, and for one of them is small, exactly lower bounds the CMI. And there are lower order terms, I guess, but yeah, that's it. And our main result, our main like as technical stuff, is showing that this is exactly, for example, for strongly convex, it's exactly 1/epsilon. And the result for membership inference is that is the same flavor, showing that whatever algorithm does, it needs to have their 1/epsilon sample with large correlation, and we can detect it with simple like the inner product test. Okay, what are the takeaways? What we observe here is that we have a very bad memorization, right? You memorize all the samples, but the algorithm is like achieve excess error of epsilon, right? This is learn. Algorithm learns in the best possible way, but memorization is like the inherent, right? So what we show is that memorization doesn't make the learning algorithm not generalized. This is the first takeaway. Another takeaway that I also really like to think about is that sometimes I feel that with differential privacy is, some people say, oh, it's very strict notion. Yeah, I'm okay with leaking one sample and this is stuff. But this result is saying that when differential private learning is not possible, there are scenarios that the membership of many samples are going to leak. And another thing is that this is also something I've worked for during my PhD, is that for some learning problem, information theoretic measures are not right measure for studying generalization. And yes, that concludes my talk. Thank you for your attention.
Thanks for the talk. If there is any question, feel free
Thank
to.
you very much.
Thank you. Thank you for invitation again.
I had one question about the membership inference result. So as part of that proof, do you construct an like efficient adversary that has an efficient algorithm that can do membership inference attack?
Yeah, the adversary is very silly, just inner product. This is the adversary.
The adversary.
This adversary even doesn't need to know like the algorithm. It just take output. And you may ask me, oh, adversary needs to know mu, right? Mu is unknown data distribution. But we show that if you give me one sample from a data distribution, one sample, I can estimate mu to the right precision, meaning that adversary also doesn't really need to know data distribution.
Was mu the expectation of Z?
Yes, yes.
But like, what do you mean by one sample you can estimate?
Let's say I give you one sample. You just use it. Let's say I give you one sample that was not part of a training set and use it as a proxy for mu.
You can just use it as a proxy.
Yeah.
Let's see.
Let's see. No. With one, see? I need to check. I'm not completely sure it's like one sample.
Mm-hmm.
Yeah, but it's also not dimension dependent sample. Probably it's going to scale with epsilon, with the excess error. But I will send you a message. Let me check. Yeah.
Okay. Sounds good. Thanks.
Thank
Are
you.
there any other questions? If not, thanks again for coming to the seminar.
Thank you. Hope to see you guys in person, hopefully.